Hello guys, welcome once more to another video on our YouTube channel. So in this video we are going to look at the Littoral regional mock of 2020 equation from further maths paper 2. Now this question is from sequences and series, recursive sequences specifically, and it was question 10. So this question was kind of sent in the MAFA further maths revision group by a student who was asking for the solution. So I thought it wise to just do a video explanation, because I think if I do a solution and send, some other students might also come and be asking for explanations, and it's going to be double work. So I better just do everything in a video. So if you are new to this channel, make sure you subscribe to this channel, you like the video, you share the video with your friends, and you also comment in the comment section. If you have any question you want me to solve, you can send the question to me directly on WhatsApp. Alright, so let's get started with the first part of the equation. So you have been told you consider two sequences un and vn defined by this. u0 is 1, un plus 1 is 2 un vn on un plus vn, v0 is 2, vn plus 1 is un plus vn on 2. Now show that un and vn are strictly positive sequences. So I think the best way to approach this is by induction. Alright, so we are going to prove this by induction. We are going to prove this by induction. Now if this video doesn't appear clear to you, if it is blur, try to increase your YouTube resolution power to maybe 360 or 480 so that the video becomes clearer, because sometimes some devices misbehave and the video doesn't appear clear. Okay, so we are going to prove this by, let me specify, mathematical induction. Now for mathematical induction, we start by looking for the statement. So let P of n be the statement un is positive, which means greater than 0, and vn is positive, which means also strictly greater than 0. So this is my P of n for all values of n, for all n in the set of natural numbers. Okay, now the very first thing to do is we need to consider the base case. In this base case, we have to verify that the statement is true for the first value of n. So verify that p0 is true. Now what does it mean? It means that we have to verify that u0 is greater than 0 and v0 is greater than 0. Now u0 is actually equal to 1, which is greater than 0, and v0 is equal to 2, which is greater than 0. Hence the statement p0 is true. So the base case is verified. Now the next thing is the induction hypothesis. So induction hypothesis. Now here we have to assume that the statement is true for n equal to some k. So assume that p of k is true. Now what does it mean by saying p of k is true? P of k is basically the statement uk is greater than 0 and vk is greater than 0. Now the next thing is the induction step. Now in this induction step, we are proving that pk plus 1 is true. That is, the statement is true for n equal to k plus 1. So we are proving that pk plus 1 is true. Now I'm just going to highlight, we have to prove that uk plus 1 is greater than 0 and vk plus 1 is greater than 0. That is what we have to prove. Alright, so let me just try to put it here so that once we prove that, we can be satisfied that we are done with it. Okay, so to prove that uk plus 1 is greater than 0 and vk plus 1 is greater than 0, we need to begin with what uk plus 1 is, right? So what is uk plus 1? If you go back to the original question, uk plus 1, you can just get uk plus 1 by replacing the n here with k. So uk plus 1, oh, Okay, uk plus 1 is equal to 2 times uk times vk divided by uk plus vk, right? And so this is uk plus 1. Okay, now let me just try to shift it down. You realize that for me to prove that it is positive, I must use my induction hypothesis, because my induction hypothesis carries information about uk and vk. So we have to note that since my uk, right, is greater than 0 and my vk is also greater than 0, then we have that uk times vk will also be greater than 0. That one is clear. When you're multiplying two positive quantities, the result will be positive. So this therefore means that for me to have my numerator of uk plus 1, I'll just have to multiply both sides of the inequality by 2, and since 2 is positive, the inequality sign will remain greater than. So it therefore means that 2 uk times vk is also greater than 0. Alright, now let's keep that man. Now let's look at the denominator. Now we also know that uk is greater than 0 and vk is greater than 0 from the induction hypothesis, because we are assuming that these two guys are both greater than 0. The statement is true. So uk is greater than 0 and vk is greater than 0. Then if I add two quantities that are both positive, the result will be positive, right? So I think we can conclude that therefore this man is true, because this guy is just the ratio of two positive quantities. So the numerator is positive, the denominator is positive. It therefore means that the ratio will be positive. Okay, now let's go to vk plus 1. Now you clearly see that our vk plus 1, according to the equation, will give us uk plus vk divided by 2. Okay, so also since our uk plus vk is positive, I'll divide both sides by 2, and I'm going to have uk plus vk divided by 2 to be greater than 0 on 2, but 0 on 2 is just 0. Now the left hand side of the inequality is just vk plus 1, right? So vk plus 1 will be positive. So since uk plus 1 is positive and vk plus 1 is also positive, then the statement p of k plus 1 is true, and then we have completed the proof by induction. So that is it. Alright, if there is any question, the comment section is open for you. Let's go to the next question number 2. Let me go to the equation. Another sequence wn is defined by this. So wn is vn minus un. Show that. So we have before that, let me just write another sequence wn is equal to vn minus un. Alright, now the second question is we have to show that 0 is less than or equal to wn plus 1 less than or equal to half wn. That's what we have to prove. Alright, so let's follow up keenly how we have to approach this question. Okay, so let's first of all look for wn plus 1. Alright, wn plus 1 is equal to vn plus 1 minus un plus 1. I just have to replace n with n plus 1 in wn. So I just need to replace n here with n plus 1, the n with n plus 1, and the n with n plus 1. Now if we try to simplify, okay, you realize that wn plus 1 will be equal to, now what is vn plus 1? Vn plus 1 is just this. Okay, vn plus 1 is un plus vn divided by 2 minus what is un plus 1? Un plus 1 in the denominator is un plus vn, and in the numerator is 2un vn. So let's start simplifying. We start by looking for the LCM, and then so the LCM is just 2 times un plus vn, right? That's the LCM. If we take this and we divide by 2, we just get a un plus vn, and we multiply with itself, we are going to get un plus vn all squared, minus, now if we take this and we divide by un plus vn, we get 2. When we multiply with this, we get 4 un vn. So this means that wn plus 1 is equal to this. Alright, so let's continue. This means that wn plus 1 is equal to, my denominator, we just keep it the way it is. Okay, now let's go to the numerator and expand. If I expand the first quantity here, I'm going to have un squared plus 2un vn, then plus vn squared. Then now we need to subtract 4un vn. Now if we bring like terms together, you realize that you are going to have un squared, okay, plus vn squared. Now 2un vn minus 4un vn just gives you negative 2un vn. Okay, it gives you negative 2un vn. Now look at the numerator. The numerator is kind of like a perfect square. Let me try to remove this man from here and place it at the end. Okay, and then you see what I'm saying. The numerator here is a perfect square, all right, and we are going to see what that perfect square is. Now you realize that let's proceed. So we are here, this man is equal to, you just have to copy this, come and paste. Now this numerator is the same as un minus vn all squared. If you expand, you are going to have un squared minus 2un vn plus vn squared, as you clearly see. Alright, now according to you realize that first of all, let's go back to the proof. We need to prove that wn plus 1 is first of all greater than 0 before less than half wn. So let's begin with the fact that, so let me say 0.1. You realize that since un is greater than 0 and vn is also greater than 0, then we have that un plus vn is greater than 0. Okay, 0.2. We have that un minus vn all squared is always greater than 0. Alright, you can, always greater or equal to 0, because un could be equal to vn, nobody knows. So because we don't care about what is inside here, okay, even if what is inside here is negative, once we square it, it becomes positive. Okay, so we realize that the numerator is positive and the denominator is also positive. It therefore means that the ratio will be positive. So therefore we have wn plus 1 being greater or equal to 0, which in turn means that 0 is less than wn plus 1. Alright, so we can keep this man first, equation 1. Now we have to prove, we have already proven this section. Now we have to prove this other section. So how do we go about it? Now we have that wn plus 1 is equal to, I am going to simplify it and I'm going to come out with wn. Okay, I'm going to come out with wn. So this wn plus 1, since it is this, right, we could rewrite it as, now what is wn? Wn is where is it? Wn is Vn minus Un. Okay, so I will first of all try to rewrite this. I'm going to have, since there is a square there, my denominator, I'll still have this. Now let's go to the numerator. If I factorize a negative sign from the interior bracket, I'll be left with Vn minus Un. Okay, because if I multiply the negative sign by Vn, I get negative Vn. If I multiply the negative sign by negative Un, I get Un. So I've not changed anything. So when I square this negative sign, it becomes positive. So at the end of the day, I could still rewrite this as Vn minus Un without any problem. So I could rewrite this as Vn minus Un all squared. Okay, now again, I'm going to rewrite it this way. I'll put a half outside because the half is my proof already. Alright, now after putting this half outside, what next? I'm going to put Un plus Vn here. Then I am going to put Vn minus Un. Alright, then again, after doing this, I am still going to multiply it with Vn minus Un. I'm doing this because, in fact, let me combine the half with this. Okay, let's try to, I'm doing this because my proof has half Wn. So that's why I'm doing this. So because my proof is having half Wn, I need to first of all bring out the half Wn first before I try to see what to do. So when this man multiplies with this man, it gives it all squared. Now there's a common denominator and then there is a half. So you have not changed anything. So this quantity here is half Wn. Alright, so we are going to have half Wn, then times, we now need to multiply with this factor. Okay, now we now need to introduce the inequality. How do I introduce the inequality? I think the best way to do is, we know that if I take Un, right, or if I take Vn and I'm adding it to Un, the result will always be greater than taking Vn and subtracting from Un. I think this one is very clear. If I take Un, right, and I'm adding it to Un, since Un is positive, okay, it will be always bigger than taking the very Vn and instead removing Un. I think it's logical, right? So this means that if this happens, this means that it means that I can divide both sides by Un plus Vn. Okay, and when I'm dividing both sides, I'm going to have here 1, alright, greater than or equal to. Now the inequality sign will not change because I'm dividing both sides by a positive quantity. This man is positive, we saw it from the beginning. So we have Vn minus Un divided by Vn plus Un. Now if 1 is greater than something, it means that that thing is less than 1. If 1 is greater than something, it means that the thing is less than 1. Okay, now see what I'm going to do next. You realize that I have now created an inequality. Okay, now for me to have everything here, I'm going to multiply both sides by half Wn. Okay, so if I multiply both sides of the inequality by half Wn, this is what I'm going to get. I'm going to have that half Wn times this quantity to be less than or equal to half Wn times 1. Now the inequality sign will remain less than because Wn is positive. See, if Wn plus 1 is positive, if the n plus 1 term is positive, it means the n term is positive, because I can just subtract 1 from here, alright, and automatically I get Wn itself to be positive, so the inequality sign will not change. So you realize that my left hand side, this quantity here, is my Wn plus 1. This is it. My Wn plus 1 is equal to everything. So from there, I think we can now just conclude that it means that Wn plus 1 is less than or equal to half Wn. We can call this equation 2. Now we can need to combine the two equations together. So the first one is 0 is less than or equal to Wn plus 1, and then the second one is the Wn plus 1 is less than or equal to half Wn. So it therefore means that Wn plus 1 is between 0 and half Wn. So that's what we're required to prove. So if there's any question, the comment section is very open for you. Alright, so let's proceed to the next question. Next question: prove by mathematical induction that Wn plus 1 is between 0 and half to the n. So prove that it is between 0 and half to the n. Okay, so we have to, I think here's the third question: proof by mathematical induction that 0 is less than or equal to Wn plus 1, less than or equal to 1 over 2 raised to the power n. Alright, so I think I already explained mathematical induction before, so I'm going to be kind of a little bit faster now. So first things first, we start by let P of n be the statement we are proving. So be the statement this. I think this is for all n in the set of natural numbers. Okay, now first thing, what do? We have the base case where we have to verify that P0 is true. Now what is P0? P0 is the statement 0 is less than W1, because I'm replacing n with 0, so this becomes W1. I'm replacing n with 0, so this is going to be 2 to 0, which is 1, so everything here is going to give us 1. So let's first of all find W1. W1 is equal to V1 minus U1. Okay, but V1 was 2, I think. Yeah, V1 is no, we are dealing with yes, we need to find V1. Yeah, we need to find V1. So V1, let's look for V1, replacing n with 0. V1 will give us U0 plus V0 divided by 2. Alright, because we need to replace n with 0 to get V1, and we need to replace the n and the n here with 0. So we need to take U0 plus V0 and we divide by 2. U0 plus V0 is 3 divided by 2. So V1 is 3. So V1 is equal to 3 on 2. Sorry, 3 on 2 minus. Now, what about U1? U1, we need to replace n with 0 here so that we get U1. So we're going to have 2 times U0 times V0 divided by U0 plus V0. So we need to take 2 times 1 times 2. So 2 times 1 is 2 times 2 is 4. So the numerator will be 4 and the denominator will be 3. So it is 4 divided by 3. So minus 4 divided by 3. Okay, so the LCM is 6. 6 divided by 2 is 3. 3 times 3 is 9. 6 divided by 3, so 4. So this one gives us 5. Alright. Okay, now we clearly see that since 0 is less than or equal to 5 over 6, 5 over 6 is bigger than 0, and it is less than 1, right? It therefore means that as 0 is less than or equal to W1, less than or equal to 1. Because when we replace n with 0 here, alright, we get 1. We replace n with 0, we get W1. We get W1, yes, and then here is 0. So P0 is a statement 0 is less than W1 less than 1, and it is clear. So hence P0 is true. Now the next thing is the induction hypothesis. Induction hypothesis. Now here we have to assume that P of k is true. P of k is true. Now this means that P of k is a statement 0 is less than or equal to wk plus 1, because we are basically replacing n with k. Wk plus 1 less than or equal to 1 over 2 raised to the power k. So this statement is true. Now the next thing is the induction step, where we are actually applying, where we are actually proving. So induction step, here we have to prove that pk plus 1 is true. That is, we have to prove that 0 is less than or equal to, if I replace n with k plus 1, n plus 1 becomes k plus 2, because it will be k plus 1 then plus 1. So we need to prove that wk plus 2 is between 0 and half. Now I need to replace the n here with k plus 1. Alright, this is what we need to prove. Okay, I think we just have to take it to the next page, because there is no space again. Okay, so I must begin with wk plus 2. Alright, so wk plus 2 is equal to vk plus 2 minus or let's see what we can do here. Let us see what we can do here to get what we have. Anyways, I think we have to prove, we have to use our previous knowledge about let's go to the, okay, I think we need to use this fact, right? We need to use this fact. We know that 0 is between, we know this, so because it is true, we have proven it already. So we know this, right? So we just need to replace the n there with k. So this means that 0 will also be less than, 0 will be less than or equal to wk plus 2, less than or equal to half times wk plus 1. I'm just replacing k here. I'm replacing k with k plus 1. Okay, so this becomes k plus 2, and then this becomes a k plus 1. Alright, so this man is very true because the original statement is true, so it's going to be true for all the terms. Okay, now what happens in my induction hypothesis is that my wk is already between 0 and 1 over 2 to the k. So since from the induction hypothesis, we have that 0 is less than or equal to wk plus 1 less than or equal to 1 over 2 raised to the power k. Alright, now my wk plus 2 is less than half wk plus 1. So you see, wk plus 2 is less than or equal to half wk plus 1, and this very wk plus 1 is also less than 1 over 2 to the k. Alright, so everything here, let me just continue in the next line with the less than or equal to. So it therefore means that my wk plus 2 will be less than or equal to half. Now what is wk less than or equal to? 1 over 2 raised to the power k. Alright, so it therefore means that my wk plus 2 is less than or equal to, we need to add the powers because they have the same base, k plus 1. This is just transitivity. Okay, so I just replace this wk plus 1 with this man because I continue with the inequality sign less than. Alright, so that is it. Now you realize that let's indicate from the beginning 0 less than or equal to and 0 less than or equal to. So this is what we have to prove. So the statement is true. Hence p of k plus 1 is true. So we are done. You can conclude. There's no time to conclude. Okay, let's go to the next part of the equation. hence deduce the limit of Wn. Alright, so since we have 0 is less than or equal to Wn plus 1 less than or equal to 1 over 2 raised to the power n, therefore means that 0 will be less than or equal to Wn less than or equal to 1 over 2 raised to the power n minus 1. For me to move from Wn plus 1 to Wn, I'm shifting one step behind, and that is just replacing n here with n minus 1, so that the 1 is going to cancel. So I need to replace n here with n minus 1. Now we are going to apply the sandwich theorem. Alright, so the limit as n tends to positive infinity of 0 is 0, because 0 is a constant. Now again, the limit as n tends to positive infinity of 1 over 2 to the power n minus 1 is also 0, because the denominator will be going to the positive infinity, so the reciprocal will be going to 0. Therefore, from the sandwich theorem, from the sandwich theorem, from the sandwich theorem, the limit as n goes to plus infinity of W0 of Wn is equal to 0. So that's what the theorem is saying, that if something is bounded between two other things, and those two other things have the same limit, therefore the limit of that thing is that limit. Okay, so we have deduced. D, here is D. You have to study the monotony, show that Un and Vn are of opposite sense of variation. So number 4, show that Un and Vn are of opposite sense of variation. That's a monotony. Alright, so monotony is just, is it increasing or is it decreasing or is it constant? So in essence, we must show that either Un is increasing and Vn is decreasing, or vice versa. So let's begin. How do I show that? How do I even test the monotony of a function? I must do the difference between the n plus 1 term and the n term, or the ratio between the n plus 1 term and the n term. In this case, it is better to do the difference between the n plus 1 term and the n term. So let's begin with Un plus 1 minus Un. Un plus 1 minus Un is equal to, now our Un plus 1 is 2Un Vn divided by Un plus Vn, then minus the Un. Alright, this is Un plus 1. Now my Un stays. Now the LCM is Un plus Vn. Now when we divide, we are just going to be left with 2Un Vn minus Un times Un plus Vn. Now let us simplify. Alright, so if I simplify, my denominator still stays as Un plus Vn. My numerator, I have 2Un Vn minus Un times Un is Un squared. Negative Un times Vn is negative Un Vn. Okay, now we basically have to bring like terms together. So that's what we have to do. So this means that this is equal to, my denominator stays intact, my numerator, if I take 2Un Vn minus Un Vn, we are going to get Un Vn. Then we need to subtract Un squared. Now from the two terms in the numerator, Un is common. Okay, so Un being common, if we factorize Un, from the first term we'll be left with Vn, and from the second term we'll be left with the Un. Alright, okay, now I'm going to rewrite this as Un divided by Un plus Vn times, guess, Wn, because this man here is Wn. Now let us check the sign, okay, because For the monotony, we are looking for the sign of this difference. If the sign is positive, then the sequence un is increasing. If the sign is negative, then the sequence un is decreasing. Now, my wn is positive, right? We proved it already. If we already had, I think, where is it? Here is it, right? We already have that wn is greater than 0. Alright, now un is positive, un plus vn is positive. So what do we have? We have that everything here will be positive, because this man is positive, this is also positive, and this is positive. So in the whole, you need to write down that justification. So everything here is positive. It could also be 0 because this wn here could be 0. Alright, now let's go to vn plus 1 minus vn. Now what is vn plus 1? Our vn plus 1 was un plus vn on 2. That's vn plus 1. Now we need to subtract vn. The LCM is 2. We have vn, we have un plus vn minus 2vn after finding the LCM. Okay, now we have 2 here, so we are going to have un. Okay, vn minus 2vn is negative vn. Now you realize that if you factorize a negative sign, okay, we are rather going to have vn minus un in the numerator. This negative sign here is going for everything here. So once we multiply by negative, we arrive here. But what is vn minus un? It is wn. So this is equal to negative half times wn. But since we know that wn is positive, right, negative half is negative. So negative half, which is negative, times wn, which is positive, will result to something which is negative. So yeah, it's going to result to something which is negative. So from there, I think we can conclude that hence un is increasing since un plus 1 minus un is positive, and vn is decreasing since vn plus 1 minus vn is negative. So they have opposite sense of variation. One is increasing and the other is decreasing. Now what can we deduce? What we can deduce is that they are adjacent. These sequences are adjacent, because an adjacent sequences are sequences that are defined recursively such that one is increasing and the other is decreasing. So, and when they are adjacent, they converge to the same limit. They converge to same limit. All right. Show that the sequence unvn is a constant sequence. So that's the fifth question. Show that the sequence unvn is a constant sequence. Okay, so if a sequence is constant, all right, it means that each of all terms are the same. You see, when you are increasing, the term before you is bigger than you. That is why when we take the difference, it's positive. When you are decreasing, the term before you is less than you. That's why when we take the difference, it's negative. When you are constant, you and the term before you or after you are all the same. Okay, so we just have to show that. So note, we just have to show that un plus 1 times vn plus 1 is equal to un times vn. Alright, or in fact, let me try to clarify your doubts. If I let t of n to be equal to un vn, okay, then you realize that if t of n is constant, then tn plus 1 is equal to tn. All the terms are the same, so we need to use the n plus 1 term and the n term. And what is tn plus 1? It is un plus 1 times vn plus 1. What is tn? It is un times vn. So this is what we have to show. Okay, so let's go on to prove. Let's go on proving that. So then let us look for un plus 1 times vn plus 1. So this is just equal to, now my un plus 1 is 2un vn divided by un plus vn. What about my vn plus 1? It is un plus vn divided by 2. You realize that 2 cancels 2. Okay, un plus 1 cancels un plus 1. What will be left is un vn, which is equal to un vn. Hence, the sequence t of n is a constant sequence. And when you are constant, there's a property. Your limit is any of your terms. Mathematically, we are saying that because that sequence is constant, then the limit, and the limit of the sequence is the limit at infinity, the limit of this sequence is equal to the first term or the second term or the third term and whatsoever. Alright, so that's just a recall. Let's go to question 6. Obtain the limit of sequences un and vn. Alright, obtain the limit of the sequences un and vn. Okay, so how do I obtain the limits of those sequences? First of all, we know that they converge to the same limit, okay, because they are adjacent. So let L be the limit of un and vn. That is, we are saying that the limit of un is equal to L, and the limit of vn is also equal to L, because they are adjacent. Okay, now with this, since we know this, okay, this just means that the limit of what is tn is un times vn. What is t0? It is u0 times v0, and it is 1 times 2, which is 2. So this means that the limit of un times vn is equal to 2. But from the properties of limit, we just have that the limit of un times vn is the same as the limit of un times the limit of vn, and is equal to 2. So if I replace those respective limits with L, we are going to have that L squared is equal to 2. So it means that L is equal to the square root of 2. We ignore the negative because the sequences are positive, so their limits cannot be negative. Okay, in a nutshell, I don't know if we can do something else again. Let's try. I've thought about an alternative method. Alternatively, let me just, if it does not work, then no problem, but let's just test an alternative method. These two sequences converge. Yes, they converge because they are bounded and they are monotonic. Yeah. Okay, now if the limit of a sequence exists, so first of all, I want us to know that the limit of un is L. It is also the same as, is also equal to the limit of un plus 1. Okay, Now let's just call the limit of Vn to be something else. Let's say the limit of Vn is L prime. Alright, so this is also equal to the limit of Vn plus 1. Yes, because they converge. Now what does this mean? This means that since this is my Un, so the limit of Un will be just 2 times the limit of Un plus 1 is equal to the limit of this man. So just have 2L times L prime divided by L plus L prime. So it means that 2L L prime divided by L plus L prime is equal to L, because that's the limit. Okay, so if we cross multiply, we are going to have 2L L prime to be equal to L times L plus L prime. Now L is going to cancel with L. Okay, and then from here, what do we have? We have that 2L prime minus L prime is equal to L, which means that L prime is equal to L. So L prime is equal to L. Anyways, I think if L prime is equal to L, then the problem is solved. Yeah, so they'll definitely have the same limit, which is good too. So this I wanted to just to verify to be sure. Alright, so thank you guys for watching. We have come to the end of this video. If the video was good, make sure you like the video. If you understood something, make sure you also comment, tell us how you feel about the video. If you have any question you want us to solve and propose a solution, you get to me